we're going to show an extremely exciting video about this, okay? So I'm going to show the videos now. There's 3 of them, and then there's also slides that you can go and look at as well. These, I think, the nerve ones were really cool. These ones are off the chart. And again, the reason I think they're the best is because you get the 3-dimensional aspect of what's going on. And plus the narrator's voice is exceptionally soothing. Is it you? It's not. It's a woman's voice. You can listen to it on your motorcycle on the way down, right?
Possibly.
Very calming.
That's actually not a bad idea. Other than not
Podcast.
being surroundings.
Dusty listens to podcasts on the way into
Game of Thrones podcast.
Known as action potentials, travel from the brain or spinal cord to trigger the contraction of skeletal muscles. An action potential propagates down a motor neuron to a skeletal muscle fiber. The site where a motor neuron excites a skeletal muscle fiber is called the neuromuscular junction. This junction is a chemical synapse consisting of the points of contact between the axon terminals of a motor neuron and the motor end plate of a skeletal muscle fiber. The events at the neuromuscular junction occur in 7 coordinated steps. Step 1. An action potential travels the length of the axon of a motor neuron to an axon terminal. Step 2. Voltage-gated calcium channels open and calcium ions diffuse into the terminal. Step 3. Calcium entry causes synaptic vesicles to release acetylcholine via exocytosis. Step 4. Acetylcholine diffuses across the synaptic cleft and binds to acetylcholine receptors, which contain ligand-gated cation channels. Step 5. These ligand-gated cation channels open. Step 6. Sodium ions, shown here in red, enter the muscle fiber, and potassium ions, shown here in blue, exit the muscle fiber. The greater inward flux of sodium ions relative to the outward flux of potassium ions causes the membrane potential to become less negative. Step 7. Once the membrane potential reaches a threshold value, an action potential propagates along the sarcolemma. Neural transmission to a muscle fiber ceases when acetylcholine is removed from the synaptic cleft. This removal occurs in 2 ways. 1. Acetylcholine diffuses away from the synapse. 2. Acetylcholine is broken down by the enzyme acetylcholinesterase to acetic acid and choline. Choline is then transported into the axon terminal for the resynthesis of acetylcholine.
That's pretty sweet, isn't it? Have you seen that video before?
No.
Yeah. So play it over and over again. Okay? It is exceptionally well done. So some things that I like about it. Let's redo it, and I'll turn the voice down. She's very soothing, though. Okay?
Foster.
Yeah. The first thing that I like about it is you get to see the impulse as it travels down that myelinated fiber. So watch the firing going down the myelinated fiber. That's hard to reproduce in a textbook. So you see it, boom, 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 boom. Okay? That would be much slower in an unmyelinated fiber. The other thing that you notice is the sarcolemma, which is the membrane of the skeletal muscle, behaves just like what? Sodium rushes in, potassium rushes out, generates an electric potential that has to reach a threshold before it fires across the whole membrane. What's that very similar to? That's a nerve, right? We're taking that electrical impulse from the neural system and we're transferring it to the skeletal muscle so that we can initiate muscle contraction. So the sarcolemma is going to behave just like that nerve fiber. What was interesting about that when you have it, when that comes down, what did you notice about the direction of that depolarization? It went entirely in both directions, didn't it? Okay? How did it work in a nerve fiber? We wanted to go unidirectional, right? We wanted to go down, and then actually there was a refractory period that wouldn't allow us to have that neuron fire after a certain point, so it would have to go down the neuron. Here, we want that electrical impulse to go over the entire skeletal muscle cell layer and go down into the skeletal muscle to initiate that contraction. So we don't want it to be unidirectional, we want it to go both ways, okay? Acetylcholine binds to these receptors. I think that's a great way. You actually get to physically see how receptors work and how these channels work, okay? Sodium comes in, potassium goes out, changes the resting membrane potential of the sarcolemma until it reaches a threshold, then it's going to depolarize.
Is a single sarcolemma associated with a single motor unit?
So say that again.
Is a single sarcolemma that is attached to those determinants of the axons associated with a single motor unit?
So you tell me.
I'd say yes. That I can initiate the contraction all at one time.
Who would agree with Austin on that? So let's go back, this picture right here. Austin should answer that question for you. So, first of all, tell me what a motor unit is.
A single integration of a neuron to a bundle of muscles or muscle fibers.
So, then your question is what?
That a single sarcolemma is associated with a motor unit or a multiple sarcolemma within those fibers.
So answer your own question. You know the answer.
That's a yes.
So let's take a look at that right there. So that is one. Pause it right there. Okay. So that's one myofibril being innervated by a neuron. So where's the sarcolemma? Surrounding that myofibril, right?
Correct.
So if I have more motor units in there, are they going to have one sarcolemma or are they going to have multiple sarcolemmas around each myofibril? That's exactly right. Is that what the question that you were asking? Okay. That's exactly right. Because now when you think about that is in the picture that we showed of a motor unit, it was the number of fibers that you innervated, right? And so we showed this picture where there was 2 motor units, right? And there was, I think, 5 and 6 or maybe 5 and 4 in there. And so each one of them had these motor end plates that were hooking up to these fibers, right? So they couldn't be one myofibril with one sarcolemma. So each one of them has this going on at that. Does that make sense?
Yep. So those motor end plates goes from one neuron or multiple?
Usually, it depends on it. I mean, this one is from one neuron, yeah. So not multiple neurons, yeah. Lance, I think your hand's up first.
So, like for me to like completely flex my elbow, is that one impulse or is it like a bunch in succession from one another?
It's a bunch of them. So,
Okay.
and we're going to show you that here in a minute too.
Okay.
So that's the other thing that I think that's lost about this is how does this work? So now you think about this. Let's go back to, let me pull up the slide presentation of the neuron. Great questions. That was chapter what? Anybody remember chapter 3 was neurons, right?
For sure.
You're not holding those in, are you, Carmen? Let those babies go. That'll kill you. Where were we talking about motor units? Anyone? Anyone?
Motor units is chocolate.
Boom, there we go.
It's chocolate.
So that should answer your question right there too, Lance, right? So if we're talking about, this is motor neurons, these are myofibrils. So this answers Austin's question, is the sarcolemma. For each myofibril, the sarcolemma is intact, but you can see that there's multiple motor end plates going to that muscle fiber, to each one, right?
But a single.
But it's a single neuron. But each, what we were watching at, the video we watched was here, 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 here. So it could have been coming down a single neuron, but each one of those was acting differently on the motor end plate. And so, Lance, the question you have, is it a continuous firing of that? Yes, you want all those muscle fibers working together, right?
Mm-hmm.
But how are we going to recruit them? When you do a muscle contraction,
The smallest ones first.
smallest ones first, then we go to the,
The bigger ones.
it's on the size
Exphys,
principle,
yeah.
right? So we go to the smaller, slow twitch fibers are recruited first, then our fast fatigue resistant, and then fast fatigue.
Will the same fiber get stimulated a bunch of times over and over and over throughout the movement?
Tell me that.
That's what I think probably, right? Just because.
You guys know the answer to this question because you've taken anatomy and physiology. Let's go on to our next video. Okay? We'll put it together. So we just are at the motor end plate, right? Impulse was coming down the neuron. Electrical impulse was transferred to the muscle. No, do you have a question?
Yeah, so in that video, it's showing the innervation of a myofibril, right?
Mm-hmm.
And then in the picture, we're showing innervations of muscle fibers, where the motor
This one?
neuron is actually attached to the fiber. So I'm getting confused on.
So let's go back to these. Are they at, so what is this right here?
Isn't that
That's a myofibril there.
Okay.
Yeah.
So yeah, because when we were talking about it, we said the motor neuron and the number of muscle fibers.
Fibers. Yeah. So that actually myofibrils is what it should be. So let's go back to this video.
Bless
You
you.
want to see the neuromuscular, or you want to move on? Now that you had the sweat, you want to see it again?
Oh no.
You can do that one. Okay, so we're going to go on now to the next one. I think this is going to help you guys figure out what's going on here. And I think, again, these are exceptionally well done. Go back, review them yourselves, look at them. This one's got the, okay? So now we're at the excitation, contraction, coupling. Okay, so we're in the skeletal muscle. We've already had the...
Typically, a single motor neuron arising in the brain or spinal cord conducts action potentials that travel to hundreds of skeletal muscle fibers within a muscle. The sequence of events that converts action...
Good Lord. So that, when you turn it up, or turn it down, it goes up. And now it's just not doing anything at all. Transferred that down to Dean's office. Let's try it again. See what happens. Woo, blew me out.
potentials in a muscle fiber to a contraction is known as excitation-contraction coupling. If we look at a single muscle fiber, we see that an action potential travels across the entire sarcolemma and is rapidly conducted into the interior of the muscle fiber by structures called transverse tubules. Transverse, or T-tubules, are regularly spaced enfoldings of the sarcolemma that branch extensively throughout the muscle fiber. At numerous junctions, the T-tubules make contact with a calcium-storing membranous network known as a sarcoplasmic reticulum, or SR. Where it abuts the T-tubule, the SR forms sac-like bulges called terminal cisternae. One portion of a T-tubule plus two adjacent terminal cisternae is known as a triad. The membranes of the T-tubule and terminal cisternae are linked by a series of proteins that control calcium release. As an action potential travels down the T-tubule, it causes a voltage-sensitive protein to change shape. This shape change opens a calcium release channel in the SR, allowing calcium ions to flood the sarcoplasm. This rapid influx of calcium triggers a contraction of the skeletal muscle fiber. Thus, calcium ions are responsible for the coupling of excitation to the contraction of skeletal muscle fibers.
Questions on that? Again, I think an outstanding job. We're going to go back to your question. So I think I misled you on that one. I can't find my mouse. Where's my mouse?
Where can we find these videos?
On Canvas.
But we're on
They
Canvas.
won't be. They're not on there right now.
Oh, okay.
They will be. Anybody see my mouse? Anybody see where it's at now?
You gotta bring it over to this screen. It was just on this one.
Now where's it at? Now where's all my stuff? I don't want that. Where's my mouse? Can we see it?
Yeah,
Okay, good.
Just had it.
Got it. Fiber, sarcolemma surrounds the fiber. Filaments are inside, or the myofibrils are inside that fiber, okay? Each sarcolemma surrounds the myofibril. So when we're talking about the motor end plate, we're talking about here on this sarcolemma, which would be the fiber, okay? So it is correct in the previous slide where it's talking about the fibers. The picture just looks a little different because you're seeing the striations of the myofibril in that picture that they drew.
So the first video then would be a fiber.
A fiber that's going down because the sarcolemma, we're now talking about the myofibrils inside the fiber.
And
Okay.
so in the first video, you had the impulse coming down and then that caused the calcium to go in and then the acetylcholine was released. Is that, which then causes the muscle contraction, but then,
So no, so what does that do? So the first video is that what we were doing was getting that electrical impulse from the nerve to the muscle.
right.
Right.
The sodium release.
And to get, so we create that action potential along the sarcolemma. And so now that action potential is going to travel down into the fiber through the T-tubules,
Oh, okay.
and then that's the next video. So you'll see that fiber. So let's watch that one again.
So from the sodium is causing the depolarization of the T-tubules.
That's exactly right. So let's watch this one again. Let's watch it at 5 speed. Backwards. And did I turn the volume on?
Typically, a single motor neuron arising in the brain or spinal cord conducts action potentials that travel to hundreds of skeletal muscle fibers within a muscle. The sequence of events that converts action potentials in a muscle fiber to a contraction is known as excitation-contraction coupling. If we look at a single muscle fiber, we see that an action potential travels across the entire
Makes sense now,
sarcolemma
no?
and is rapidly conducted into the interior of the
T-tubules not
muscle
taken
fiber
inside
by
the
structures
fiber.
called transverse tubules. Transverse, or T-tubules, are regularly spaced enfoldings of the sarcolemma that branch extensively throughout the muscle fiber. At numerous junctions, the T-tubules make contact with a calcium-storing membranous network known as a sarcoplasmic reticulum, or SR. Where it abuts the T-tubule, the SR forms sac-like bulges called terminal cisternae. One portion of a T-tubule plus two adjacent terminal cisternae is known as a triad. The membranes of the T-tubule and terminal cisternae are linked by a series of proteins that control calcium release. As an action potential travels down the T-tubule, it causes a voltage-sensitive protein to change shape. This shape change opens a calcium release channel in the SR, allowing calcium ions to flood the sarcoplasm. This rapid influx of calcium triggers a contraction of the skeletal muscle fiber. Thus, calcium ions are responsible for the coupling of excitation to the contraction of skeletal muscle fibers.
Is that a little more clear now?
Yeah,
So those T-tubules, why do we need those T-tubules now?
so we can get into the actual fiber.
Yeah, because if we didn't, that action potential would just travel on the outside of the fiber, right? We wouldn't be able to get it down into each myofibril so it can contract. So the T-tubules is just an extension of that sarcolemma that allows the action potential to go down into, so that you can cause all of this to happen at each of those myofibrils.
And so the first video is almost just preceding the second video.
So this one is the first one, yeah. And so the first one, when you see it coming down and in the neuron, and then you see it going across the sarcolemma,
Right.
that's the first video.
Right.
And then
It's going down.
when we go down into it is the second video. Okay. And now there's a part in there where it says it causes contraction and the muscle contracts. Guess what the third video is? That's where we talk about specifically the cross-bridge cycling, okay? This is now what Dr. Murphy you guys probably had multiple test questions about this, didn't you? The cross-bridge cycling. So now, this is what happens at the level of actin and myosin. And I took my shoes off because my feet are
The
sunburned.
contraction of a skeletal
From wearing
muscle
flip-flops at
generates the
baseball.
force necessary to move the skeleton. A contraction is triggered by a series of molecular events known as the cross-bridge cycle. In a skeletal muscle fiber, the functional unit of contraction is called the sarcomere.
This is the best one by
A
far.
sarcomere shortens when myosin heads in thick myofilaments form cross bridges with actin molecules in thin myofilaments. The formation of a cross bridge is initiated when calcium ions, released from the sarcoplasmic reticulum, bind to troponin. This binding causes troponin to change shape. Tropomyosin moves away from the myosin-binding sites on actin, allowing the myosin head to bind actin and form a cross bridge. Also note that the myosin head must be activated before a cross bridge cycle can begin. This occurs when ATP binds to the myosin head and is hydrolyzed to ADP and inorganic phosphate. The energy liberated from the hydrolysis of ATP activates the myosin head, forcing it into the cocked position. A cross-bridge cycle may be divided into 4 steps. Step 1. Cross-bridge formation. The activated myosin head binds to actin, forming a cross-bridge. Inorganic phosphate is released, and the bond between myosin and actin becomes stronger. Step 2. The power stroke. ADP is released and the activated myosin head pivots, sliding the thin myofilament toward the center of the sarcomere. Step 3. Cross-bridge detachment. When another ATP binds to the myosin head, the link between the myosin head and actin weakens, and the myosin head detaches. Step 4. Reactivation of the myosin head. ATP is hydrolyzed to ADP and inorganic phosphate. The energy released during hydrolysis reactivates the myosin head, returning it to the cocked position. As long as the binding sites on actin remain exposed, the cross-bridge cycle will repeat. And as the cycle repeats, the thin myofilaments are pulled toward each other and the sarcomere shortens. This shortening causes the whole muscle to contract. Cross-bridge cycling ends when calcium ions are actively transported back into the sarcoplasmic reticulum. Troponin returns to its original shape, allowing tropomyosin to glide over and cover the myosin binding site on actin.
That's sweet, isn't it? So you can read that in a textbook and look at a two-dimensional figure in your textbook where it shows one myosin head or maybe two myosin head releasing. But this, to me, you get to see all those myosin heads working at different times in order to get that skeletal muscle contraction. It is elegant. It's beautiful. You can't even, you're like, why didn't I have this before? I wish I had it in graduate school. Let's watch it again. It's so good.
At the very end of that video, that's not the only time the muscle
The contraction of a skeletal muscle generates the force necessary to move the skeleton. A contraction is triggered by a series of molecular
There's
events
structural
known as the
that you
cross-bridge
can
cycle.
only get so much, right?
In a skeletal muscle
Like
fiber,
we couldn't contract our
the functional
quads
unit of
into a
contraction
ball,
is
right?
called
There's going to be structural
the
limitations.
sarcomere.
And the Z-line happens to be that structural limitation. So, and we'll talk about that in regards to how you generate force.
A sarcomere shortens when myosin
So
heads
watch all
and
these
thick
myosin
myofilaments
heads.
form cross bridges with actin molecules and thin myofilaments.
It's awesome. Because you just visualize one of them happening all the time in the textbook. And it
The
does this,
formation
it
of
does
a
this.
cross bridge
This
is
is awesome. Look
initiated
at
when
this.
calcium
People always
ions
goes, what does a
released from
conformational
the
change in
sarcoplasmic
tropomyosin look
reticulum
like?
bind to troponin.
Binds to
This
troponin.
binding causes troponin to change shape. Tropomyosin moves away from the myosin binding sites on actin,
Bind sites open
allowing
up.
the myosin head to bind actin and form a cross bridge. Also note that the myosin head must be activated before a cross bridge cycle can begin. This occurs when ATP binds to the myosin head and is hydrolyzed to ADP and inorganic phosphate. The energy liberated from the hydrolysis of ATP activates the myosin head, forcing it into the cocked position.
See that one was already cocked there
A
behind it.
cross-bridge
the
cycle
myosin
may
head.
be divided into 4 steps. Step 1. Cross-bridge formation. The activated myosin head binds to actin, forming a cross-bridge. Inorganic phosphate is released, and the bond between myosin and actin becomes stronger. Step 2. The power stroke. ADP is released, and the activated myosin head pivots, sliding the thin myofilament toward the center of the sarcomere.
Notice that one didn't move.
Step 3.
Okay.
Cross-bridge
It's going to react on
detachment.
its own.
When another ATP binds to the myosin head, the link between the myosin head and actin weakens, and the myosin head detaches. Step 4. Reactivation of the myosin head. ATP is hydrolyzed to ADP and inorganic phosphate. The energy released during hydrolysis reactivates the myosin head, returning it to the cocked position.
Now this is it. Look at
As
it.
long as the binding sites on
boom,
actin remain
boom.
exposed, the cross-bridge cycle will repeat.
As long as the actin sites remain exposed, and what else is
And
there?
as the cycle repeats, the thin myofilaments are pulled toward each other, and
Causes
the
the
sarcomere
release of the
shortens.
head, and then
This
hydrolyzes.
shortening causes the whole muscle to
ATP,
contract.
right? You have to have energy.
Cross-bridge
so
cycling
if the calcium's
ends when
there,
calcium ions are actively transported back into the sarcoplasmic reticulum. troponin returns to its original shape, allowing tropomyosin to glide over and cover the myosin binding site on actin.
Now think about that. Just doing that. How many myosin heads you think are catching, releasing, catching, releasing, catching, releasing for you just to do a simple movement with your arm? Millions, right?
And within that little bit of space right there, every time calcium stops, I imagine that's when our stored ATP goes up.
So you're exactly right. So what would happen, Austin, if there wasn't ATP available?
There's no composition, no pull.
There isn't any what? So if there's no ATP binds to that head, and what happens when it binds to that head? It releases, right? Then it hydrolyzes, so you knock off inorganic phosphate, and that energy is used to cock the head, right? But if there's no ATP, what happens? Rigor mortis. So the myosin heads stay stuck to the actin because you don't have any ATP. And rigor mortis happens when what? No?
You die.
You're dead. You're not producing ATP. So that's a way that you'd stop contracting, right? Austin also said there was one. You'll notice you're going to reach the point where if this was fiber sliding over, you can do with your hands. At some point, you can't push your fingers through your hand, right? Structurally, now there's no more sliding going on because you've reached the structural limitations of the myofibril. So that's going to stop contraction. Going to affect force production as well because there's going to be differences in overlap. But how you generate force is based upon how much overlap you have between actin and myosin, and basically how many actin and myosin heads that are going to be bound to each other to generate that force. Now think about a isometric contraction. What's an isometric? What we've been showing is what kind of contraction? That's a concentric contraction, right? So you have a muscle that's shortening. Okay, what's a contraction? Can you have a contraction that lengthens? Eccentric contraction, right? Okay. What about isometric? What's that mean? Iso, same. So that would be like you guys getting up and doing what? Trying to push the wall. Okay, so if you tried to push this wall over, could you do it? Probably not. But are you doing muscular work?
No.
Really?
Work, no.
Stand up. So are you doing muscular work?
Kind of do the definition of what work is.
So are you expending energy?
Yes.
So are you doing work? Are you producing force in that muscle?
Force, yes. Distance, no.
Not any distance. So, but you're generating that with that, right? And so you're just not doing anything. You're just up there pushing the wall, but you're contracting, right? No concentric contraction like we've seen here before, but you're still doing, the myosin heads are attached, right? As you're pushing on that. So think about all of that from a microscopic level, cellular level, when we're talking